Hello, hello, hello. This is Coach Ikram, and welcome to this video on the periodic table of the elements. In this video, we're going to be discussing the octet rule, oxidation numbers and states, and how those oxidation numbers are going to contribute to bonding. So we're going to start by talking a little bit about the octet rule. The octet rule is a man-made rule. It's not a law of nature, and the octet rule states that atoms are going to gain or lose electrons in order to secure those 8 electrons in their outermost or valence shell or energy level. And again, like I said, it's a man-made rule. It's not a law. There's going to be a lot of exceptions where atoms are going to gain less or gain more than the standard 8. And one of the main exceptions that you already know about would be the duet rule, in which hydrogen and helium don't have 8 in their outer valence shell because they're in that first energy level. They're only going to have 2 electrons in their outer valence shell. An ion, just as a reminder, is an atom or a group of combined atoms, like a polyatomic ion, that has a charge because of a gain or loss of electrons. So, for example, calcium ion or fluoride. So an oxidation state is going to be the charge on an ion or an element after it has gained or lost those electrons to fulfill the octet rule. And this can either be a positive oxidation state or a negative oxidation state. And overall, it's going to be determined by those number of valence electrons in the atom. The representative elements, remember, those are groups 1 and 2, the alkali and alkaline earth metals, and groups 13 through 18. Those are going to have predictable oxidation states we're going to be able to predict using the periodic table. If we look at the periodic table, this is kind of a, you've seen the periodic table a lot of ways. This is sort of another representation of it with colors, so you can see it clearly. These are the predictable oxidation numbers. And again, like we said, groups 1 and 2, the alkali and the alkali earth metals, and groups 13 through 18 over here. These are the oxidation numbers that you can predict. So as you can see over here are alkali metals. They have an oxidation number of +1. They're typically going to lose that 1 extra electron in that s orbital to get their octet. Alkaline earth metals are going to lose 2 electrons, because remember they are S2 is their generic electron configuration. Skipping over here to the right-hand side, the noble gases have an oxidation number of 0 because typically, remember, they have 8 electrons. They already fulfill the octet rule. Halogens, -1 because they're going to gain that 1 electron. And then group 16, -2. Group 15, -3. Group 13, remember it starts up at the top with boron and aluminum. That's going to be +3. And then these right here are those 3 exceptions to the multivalent transition elements. We have silver, cadmium, and zinc. And remember, those are +1, +2, and +2. So we're going to start by talking about how we use this in bonding. And we're going to get to a bonding unit a little bit later, but we're going to just kind of give you a brief overview so you can see the application of oxidation numbers. Ionic bonding is when you form a bond between a cation and an anion. And to refresh your memory, cations are metals and they are a positive charge, and anions are non-metals that have gained electrons and they are negative. And so, for example, down here we've got sodium and chlorine. Sodium is an alkali metal. It becomes sodium plus ion when it becomes an ion, a cation. Chlorine is a non-metal. It's in group 17. And so it becomes chloride, which is Cl -1. So that sodium, when these two interact, when that sodium loses that electron, it becomes Na+. And when that chlorine gains that extra electron, it becomes chlorine -1 or chloride. Those two are now going to be attracted to each other. And so what would end up happening is that positive cation and that negative anion would now be attracted to each other, and they're going to form a very strong bond because of that positive and negative charge. So in order to use oxidation states to form ionic bonds, we're going to follow these 3 steps right here. We're going to first determine the charge, or that oxidation state of the metal and the non-metal in question. Then we're going to write our cation with its charge and our anion with its charge. And then we're going to balance the demands of each element, and layman's term for it is swap and drop. And it's just an easy way to remember what it is that you're actually going to be doing. So some examples down here. We have sodium and chlorine, and we did this one on the previous slide. So sodium, if you look on the periodic table, it's an alkali metal, so it's going to become Na+. Chlorine is a halogen. It's going to become Cl- chloride. So if you note, sodium, for every 1 electron that sodium loses, chlorine needs 1. So So in order for these two to form an ionic bond, you're going to have one sodium and one chlorine. So for every one electron sodium loses, chlorine takes that electron. In the second one, we've got calcium and sulfur. Calcium is going to become calcium ion, which is calcium 2+. Sulfur is going to become sulfide, 2-. So if you note, if calcium loses 2 electrons, sulfur needs 2 electrons. So if you were doing swap and drop, you would theoretically make it look like that. You can also think of it conceptually. Calcium loses 2, sulfur gains 2, so you're going to need 1 sulfur for every 1 calcium. And if you do the swap and drop method, you would have ended up with this. And that's going to reduce down to calcium sulfide right there. The last one we have barium and chlorine. Barium is going to become barium ion, so Ba2+. Chlorine is going to be chloride, Cl-1. So barium is going to lose 2 electrons. Chlorine only needs to gain 1. So in order for these to balance the demands of each element, how many do you need? If barium loses 2, I'm going to draw it up here. If barium loses 2, you're going to need 1 barium, and you're going to need 2 chlorines, because chlorine only accepts 1 electron. So if barium's giving up 2, in order for chlorine to form an ionic bond with it, there's going to have to be 2 chlorines, 1 chlorine for each of the electrons that barium is giving up. So we're going to talk just quickly about covalent molecular bonding and metallic bonding in order to give you just a reference point for the difference between these types of bonds and ionic bonds. Covalent bonds are going to form when non-metals share electrons. No ions are going to actually be formed. And later in this unit, we're going to talk about the attraction between these atoms and how the electronegativity difference is going to affect that. But a very good example of a covalent bond is going to be water. So you're going to have this oxygen and then 2 hydrogens, and they're sharing electrons across these bonds. And so in sharing, they're each going to fill their valence shell, and they're each going to satisfy either the duet rule for hydrogen or the octet rule for oxygen. So if you can see here, we've got these 2 electrons are being shared, and so hydrogen has the 2 that it needs to fill the duet rule, and oxygen over here now has 8 in its valence shell if you count the 2 that it's sharing with each of the hydrogens. Metallic bonding is when you've got metals that are made entirely of periodic table metals, and these bond in a way that is sort of unique. You get your metal cations, because remember, metals lose electrons, so they become cations. So these are sitting right here. And the electrons, their valence electrons become delocalized. So instead of being in their energy shells right around that nucleus, they're going to delocalize and travel freely throughout that entire metal sample that we've got up here. They're not going to belong to any one atom. And this is going to form what we call a sea of electrons. So as you can see, no pun intended, you can see these electrons are all floating around this entire selection of metal cations. These metal cations are going to be attracted to those negatively charged electron-rich regions, and the electrons are going to insulate those cations from each other. And so what that's going to end up forming is those metals are going to form crystals because of this arrangement. And crystals are any substance whose particles are arranged in a 3D orderly pattern. You can see up here we've got a gold crystal and what that looks like. Another term that you're going to need to know about metallic bonding is alloy. A metal alloy is like brass or steel, and it's going to be made from varying amounts of different pure metals that are mixed together while they're molten. And so unique alloys, that's going to give them very special unique properties. So stainless steel, structural steel, sterling silver, like in jewelry, are all examples of metal alloys. That is the end of this video on oxidation states and the intro to bonding. Please make sure you rewatch, take detailed notes, and be ready to ask questions in class. Thanks.